we will solve one problem and implement all these 5 steps in it. And the problem is design 2-bit synchronous up counter. And the step number 1 says decide the number of flip-flops and definitely the type of flip-flop that you want to use. And you already know from the asynchronous counters, the number of flip-flop is decided on the basis of the bit of the counter. In this case, we have a 2-bit synchronous up counter. So this 2-bit is telling us to take 2 flip-flops. So we are going to use 2 flip-flops. This is our step number 1, and we have to also decide the type of the flip-flop that we have to use. And let's say I will use JK flip-flop for the designing purpose. You can also use T or D flip-flop, there is no problem. And the step number 2 says write the excitation table for the flip-flop. So we have to write the excitation table for the JK flip-flop. Let's do it. The step number 2, that is the excitation table of JK flip flop. Okay, and in excitation table we already know the input is Qn and the other input is Qn plus 1, and we have to find out the values for J and K. As there are 2 inputs, we have 4 possible conditions: 0 0, 0 1, 1 0 and 1 1. Depending upon this, we have to find J K. So when Qn is 0, this Qn is nothing but our present state, and this Qn plus 1 is our next state. So when present state is 0 and next state is also 0, so it is possible only when J is 0, K is 0, or when J is 0 and K is 1. So we will replace this K by a don't care, and we have a cross here representing K is the don't care in this case. Now we will see the next case when Qn is 0 and Qn plus 1 is 1, and this will happen when J is 1, K is 1, toggling. Whenever there is a toggling, we have to take complement of the previous state, and we will take the complement of 0 and it will give us 1. Or I can also say that J is 1 and K is 0. So definitely again K is the don't care and J is 1, so I will write J as 1 and K as don't care. In the same way we have to complete for the rest 2 cases, and I will write it directly. It is 1 0. So this is the excitation table for the JK flip-flop that we have selected to design our 2-bit synchronous up counter. So we are done with step number 1, step number 2. Now the step number 3 says draw the state diagram and the circuit excitation table, and we will first draw the state diagram. So step number 3, in this we will first draw the state diagram. So how many state will be there when we have a 2-bit synchronous up counter? It is simply 2 to the power n, and n is equal to 2, so I have 4. There are 4 states, and what is the maximum count? It is equal to 4 minus 1, that is 3. So a 2-bit synchronous up counter will start counting from 0 and end its count to 3. So this is what we have to draw in the state diagram. And I have been talking about this synchronous counter from a while, but I have not told you what is the difference between the synchronous and asynchronous counters. The difference is the clock. The clock is given simultaneously to all the flip-flops in this case, whereas in case of asynchronous counters the clock is not given simultaneously. And because of this fact that we are giving the clock simultaneously, this type of counter is little bit tough to design as compared to the asynchronous one. You have already learnt about the asynchronous counters, and you have seen that it is not that much tough to design the asynchronous counter. Generally the pattern is same, but in this case we have to follow certain steps and then we have to design the counter. So the clock is not simultaneous, and we will see it in the designing part when we will implement the obtained equations and draw the logic diagram. Now let's move to the state diagram. We are having the 4 states, so I will draw the 4 states. This is state number 1, state number 2, state number 3 and state number 4. The first state is, let's say, S0. This is S0, this is S1, S2 and S3. S0 is a 0, so 0 0, S1 is 1, so 0 1, S2 is 2, so 1 0, and finally S3 is 3, so 1 or 1. And we have to design a up counter that you can see from the problem. So definitely with every passing clock pulse it will count higher value. We are starting from S0, then we will go on S1, then S2, S3, and again the output of the two flip-flop is 0 0. This one is Q1 and this one is Q2, the output of the two flip-flops that we are going to use now. And in step 3 we have to also draw the circuit excitation table. So let's draw the circuit excitation table, and this is the most important part in the designing. And you can see that we are just following the normal step of the designing process. In the sequential circuits, we are having our state diagram, we are going to make the circuit excitation table, we will use the excitation table for the flip-flop, then we will use K-map, and finally the implementation. So the first column will have the present state. The present state is given by Q1, Q2. The column 2 will have the next state, Q1 star, Q2 star, and the column 3 now have J1, K1, and similarly the column 4 will have J2, K2. Okay, now Q1, Q2 is 0 0. Then you can see when the present state is 0 0, we are having the next state as 0 1. So Q1 star and Q2 star is 0 1. Similarly, if the present state is 0 1, the next state is 1 0. You can see the next state is 1 0. And if present state is 1 0, the next state is 1 1. And finally, if the present state is 1 1, the next state is 0 0. So we have just followed the transition that is shown by this state diagram, and we have written it in the circuit excitation table. Now by using this excitation table of the flip-flop, we have to find out the value of J1, K1, J2 and K2. So let's start with J1, K1. For J1, K1, that is the input of our first flip-flop, we have to see Q1 and Q1 star. We don't have to see Q2 and Q2 star because they are for the second flip-flop. So let's see. When Q1 is 0 and Q1 star is 0, you can see from here J is 0 and K's don't care. So J is 0 and K's don't care. Similarly, when Q1 is 0 and Q1 star is 1, from this case J is 1, K's don't care. So J is 1, K's don't care. And when they are 1 1, Q1 is 1 and Q1 star is 1, the last case, J's don't care and K is 0. So J's don't care, K is 0. And when they are 1 0, we have don't care 1. In the same way, I will complete for the second flip-flop. The inputs are J2 and K2. The output is Q2 and the next state is Q2 star. 0 1 will give me 1 don't care. 1 0 will give me don't care 1. 0 1 will give me 1 don't care, and then 1 0 again will give me don't care 1. You can compare it from this table. Now we are done with this step number 3 also, and the step number 4 comes into the action, and we have to make the K map to determine the value of J1, K1, J2, K2. As we are having the two variables Q1, Q2, we have to use a 4-cell K map. So let's make a 4-cell K map, and we need 4 such maps to reduce the values of J1, K1, J2 and K2. So the input is Q1, Q2, 0 1 0 1. I will copy this map and paste it 4 times so that we don't have to make it again. Copy and then paste. Okay, this is the third one, and finally the last K map. And first I will find out the value of J1. So this K map is for J1. Let's fill it. 0 1 don't care, 0 1 don't care, and you can see it is a very simple K map. This is the pair, and J1 is equal to Q2. Now we will do the same process for K1. K1 is don't care 0 1. So don't care 0 1. Again a very simple case. We have K1 as Q2. Now we will try to find out the input for the flip-flop number 2, that is J2 and K2. For J2 you can see 1 don't care, 1 don't care is there, so 1 don't care, 1 don't care. And for K2 we have don't care 1, don't care 1, so don't care 1, don't care 1. And now you can see if I include the don't cares, then I have the value of J2 equal to 1, and in the same way the value of K2 is also equal to 1. So we are having our values of the input, and now we can finally move to the step number 5, that is designing of the circuit. Draw the logic diagram. So we will implement it quickly. First we will make 2 flip-flops, 2 JK flip-flops. This is my first JK flip-flop, and this one is the second JK flip-flop. And as it is a synchronous counter, the clock is given simultaneously. There is a common clock, and that is given to both of these flip-flops. This is clock, and the input J1 is equal to Q2. So first I will just make the inputs, then we will do the connection. This is the output Q1, J1, K1, J2, K2, Q2, and you can see J1 and K1 both are equal to Q2. So I will just connect J1 and K1 with Q2, and J2 and K2 are 1, so J2 and K2 are 1, so I will give logic 1 here, and we will take the outputs Q1 and Q2, and these are the output of the clock that will show us the state, the present state, and the state will keep on changing. It will be first 0, then 1, 2, 3, and then back to 0, and in this way it will do a counting. So this is all for this presentation.